So over the last couple of weeks, you've learned the foundational skills that you'll need to be able to solve problems using the first law of thermodynamics. And that's exactly what we're going to do today. Thanks for coming back to thermodynamics. We're in lecture 11, and today we're going to do an example on the first law. So here's our problem statement. You can find the starter sheet on the My Courses website, but it's basically telling us the same thing. So 2 kilograms of pure water is held in the piston cylinder assembly shown here at the bottom. The water initially exists at a pressure of 1 atmosphere and a temperature of 20 degrees Celsius. Heat is added at constant pressure until the piston hits the stops. So until it gets over here. Heat addition continues until the water reaches 4 bars. So the pressure keeps increasing once we hit the stops. Find the total A, work, and B, heat transfer of the process, and C, sketch the TV and PV diagram. So in addition to the problem statement, we're also given a bunch of reference material. So we have some steam tables here for saturated water, which means that some mixture, two-phase mixture of saturated liquid and saturated vapor. We're given some superheated water data, and we're also given some data for the specific heat for a variety of different materials, including water. So if we look at our problem-solving methodology, the first thing we want to do is harvest some given information from the problem. We know that the diameter of our piston is 2 meters, that at state 1 we have liquid water at 1 atmosphere and 20 degrees Celsius, and that at state 2 our piston expands to the point where it's 1 meter away from the base. We know that at state 3 the pressure increases up to 1 bar, and we're required to find the total work of both processes, the process from 1 to 2 and the process from 2 to 3, the total heat transfer for both processes, and we're asked to sketch the TV and PV diagrams. So let's go through this together. First, I like to draw a schematic. So I have this sort of given on the sheet, but if I didn't, I would still want to draw a picture of my piston cylinder assembly and how it slides from its initial position to its final position, or its second and third positions. And I draw a base TV and PV diagrams. Now these are sort of very carefully made, these diagrams. On a test, obviously you're not expected to draw freehand on a log plot, so you just sort of are conceptually drawing what you think a vapor dome looks like. We know that process 1 is a constant pressure process. It moves from P1 to P2, and those are the same values. And the reason that we're assuming that this is a constant pressure process is because as we're adding heat, our water is expanding, and we're neglecting the forces of friction. So we're saying that there's not any extra force pushing that piston in, so there's not any extra pressure. So we're going to assume that the pressure is constant as we move from state 1 to state 2. And then at state 2, from state 2 to state 3, so remember, this second process starts once we hit the stops on the piston. So now our volume has to remain constant if that piston can't move. So we know that V3 must be equal to V2. And more than that, because this is a closed system with no mass coming in or out, we know that the specific volume, that's the volume divided by the mass, also has to stay constant as I move from state 2 to state 3. I also know that the volume at state 1 is going to be the mass times the specific volume at state 1. So my governing equation here, as will often be the case in thermodynamics, is the first law of thermodynamics. I know that the change in energy in my system from the end state to the beginning state is equal to Q that happens in that process minus W that happens in that process. Now it's important to remember here, my subscripts are 2 and 1. So I'm only looking here at the first process from state 1 to state 2. But I would do this again for the second process. And the equation for the second process would be capital E3 minus capital E2 is equal to Q from 2 to 3 minus W from 2 to 3. If we neglect changes in kinetic, potential, and spring energies, my delta E becomes change in internal energy. I know that I can find the work by taking the integral of P dV, and I'm going to use my tables to find specific internal energy, and then I'll find the change in specific internal energy for each process and multiply that by the mass, and that will give me the change in the internal energy. And I'll use all of that to find the heat transfer in process 1 and then the heat transfer in process 2. So we'll do this for both of our processes. Here I have a state table at the top, and then I've also done this process table where I'm going to write what the heat transfer in process 1 is and the work in process 1, and the same things for process 2. So I can just add those up to find the total heat and the total work. So now, how are we going to go about finding specific volume? So we know that specific volume is the volume divided by the mass. So I'm told how much mass is in my system. So let's try to figure out the volume. The volume at state 2, I'm told this is a piston cylinder assembly, and I'm given a diameter. So half of that diameter is the radius. So I can find the volume by taking the cross-sectional area of the piston, which is pi r squared, multiplied by the length. So here, now I'm getting the cross-sectional area of this piston multiplied by the length. That gives me the volume. And when I do that, I get that the volume is 3.14 meters cubed. But remember, I want to deal with intensive properties in thermodynamics. So now I want to find the specific volume, and this will be the same specific volume for state 2 and state 3 because the piston is in the same position in both cases. So I'll take this volume and divide by the mass. Now my mass is 2 kilograms, so my specific volume at state 2 and state 3 becomes 1.57 meters cubed per kilogram. So I can put that on my table, and now I'm starting to feel a little bit better because I have 2 intensive properties at each state. Now I'm hoping that they're always independent. So I know that P and specific volume are always going to be independent, but temperature and pressure are only independent if I'm not under the vapor dome. So I'll have to see what happens. So for each state, I want to figure out what is the phase of water that I'm dealing with. Is it a subcooled liquid? Is it a superheated vapor? Or is it some two-phase mixture? So I'll start by drawing on a TV diagram what my first state looks like. So here I'm told the pressure. So I know that pressure, constant pressure lines on a TV diagram start low. They increase until we hit the saturated liquid line. Then they stay flat. And then they go up. So now because this is 1 atmosphere, I also know that the temperature where this is flat, so the boiling temperature of water or the saturation temperature of water at 1 atmosphere is 100 degrees Celsius. So I put that on my table as well. Now, because my temperature is 20 degrees Celsius, now I have to look for where this 20 degrees Celsius line crosses my constant pressure line, right? Because I know 2 independent intensive properties, and I'm looking for where those 2 lines intersect on my graph. And in this case, state 1 is in the subcooled liquid region. But we already knew that because we live on Earth where the pressure is usually around atmospheric pressure, and water is not spontaneously boiling at 20 degrees if we're at atmospheric pressure. So now we know state 1 is in the subcooled liquid region. State 2, we know that it's at the same pressure because as we go from state 1 to state 2, it's the constant pressure process. But I'm not sure. I've drawn this purple line, and I guess I cheated because I know where it goes, but I don't know exactly where to draw this purple line. But this is a temperature versus specific volume graph. So what I want to know is where is the specific volume at 100 degrees where we have saturated vapor. So I look on my 2-phase graph, and I would see that Vg, so the specific volume of a saturated vapor at 100 degrees Celsius, is 1.673 meters cubed per kilogram. But my specific volume, which I calculated, is 1.57. So that's less than 1.67. So that means for state 2, I'm under the vapor dome. If my specific volume at state 2 was 2, then I would be up here somewhere on the graph. I'd have to go past 1.673. But as we're under the vapor dome at state 2. Now, as I move from state 2 to state 3, remember the specific volume stays constant because the mass stays constant, and the volume stays constant because the piston is butting up against those stops in the cylinder. So I know my second state is 2-phase. So now I want to look at my third state. So what I'm going to do here is I'm going to draw another constant pressure line. Now my constant pressure line here is 4 bar. So when we increase pressure, the shape of the line stays basically the same, where it goes up in the subcooled liquid region, stays flat under the vapor dome, and then goes up in the superheated vapor region. But what happens here is that as the pressure goes up, this line shifts up as well. So now I'm looking for the intersection on this same specific volume, the purple line, with my second blue line, and I notice again that I'm up here in the superheated vapor region because that's where these two lines intersect. So now I have state 1, which is down here, state 2, which is in the 2-phase region, and state 3, which is the superheated vapor. So the reason I like to draw these graphs early on in the problem is because it gives me an idea of which region each of my points are in. And if I know that, I'll have a better idea of which table to look on. So when I'm doing this freehand on a test or in homework, I'm not super concerned with getting it in the exact right place. I'm not going to graphically read the values off here, but I would like to know what table I'm supposed to look at. And hopefully drawing these things out helps. So we can do the same thing on a PV diagram. So here for state 1, I know a constant temperature. So here, actually, so what I've drawn first is the constant temperature at which water boils, right? So here, if we have 1 atmosphere, right? And now my constant temperature lines are going to go down and then across and then down. So they're a bit like the constant pressure lines on a TV diagram, except that they're inverted. So the slope is going the other way. So here I know for my constant 100 degrees Celsius, I'm going to start up here, go down, and then go over, right? And if I had a 20 degrees Celsius line, it's also going to shift down. Just like the pressure lines shifted up and down with pressure, the temperature lines are going to shift up and down with temperature. So the constant temperature line here would go down and then over and then down. So if I was looking for saturated liquid, it would be at this point A. But my point 1 is further over because the temperature is lower. So we'd have to take a line like this and shift it down to get our 20 degree line. So state 1 is again in the subcooled liquid region. State 2, again, we would find that at 100 degrees or at pressure is equal to 1 bar, we would have superheated, or we would have saturated vapor on the red line, which is higher than the specific volume that we get in our case. So we know state 2 is below the vapor dome. Now we would go from 1 bar up to 4 bar, and that would come up here. So when we do this, we have all the state points that we need, and we can see that no matter which way that I draw the graph, my points are in the same regions. And that's important. If you're drawing these out on PV and TV diagrams and you're getting points in different regions, that might be an indication that you're making a mistake somewhere. So now I know the phase that I'm looking for here. Only one of my points, point 2, will actually... Only one of my states, state 2, will actually have equality. So for state 1, I wrote down that this is a subcooled liquid. And for state 3, I wrote that we have a superheated vapor. So now we have enough information to find the work from process 1 to 2 and from process 2 to 3. So we know that work from 1 to 2 is the integral of P dV. So because pressure is constant, I can take it outside of the integral. So I know that work is the pressure times the integral of dV, which is just pressure times delta V. But I don't really have the volumes because I don't know the volume at state 1. So I'm going to change this. I'm going to divide that big V term by m to get two little v's, so a delta specific volume. But to do that, I have to take the m out. So now for work, I have pressure times the mass of my system, which remains constant, multiplied by V2 minus V1. So those are specific volumes. I don't know the work, but I do know pressure. I do know the mass. I do know the specific volume at 2, but I don't know the specific volume at 1. So I'm going to have to try to find the specific volume at 1. So now what I want to do, remember for subcooled liquids, we're going to make the approximation that the properties are the same as saturated liquids at the same temperature. So the specific volume of my subcooled liquid is equal to Vf at the same temperature, which here is 20 degrees. So I look on my table and I find that this is basically 1 over 1,000. Specific volume for water is usually approximately 1 over 1,000. So now I can put all this information that I know into my equation. I know my pressure is 101.3 kilopascals, or kilonewtons per meter squared, multiplied by 2 kilograms, that's my mass, multiplied by 1.57, that's my specific volume at 2, minus 1 over 1,000, that's my specific volume at 1, and the units of specific volume are meters cubed per kilogram. I'm tracking my units to make sure that I don't make mistakes here. So here, the 1 over meters squared here cancels out 2 of the meters cubed, so I'm left with just meters. My kilograms cancel, and what I'm going to get is that I have 317.9 kilonewton meters, which is the same as 317.9 kilojoules. So I can put that in my table down here, and now I know the work for process 1. But what about the work in our second process? So as I move from state 2 to state 3, I can use the same equation, that work is the integral of PdV from V2 to V3. Now the cool thing about this process is that the volume stays the same, and when the volume is constant, we get my absolute favorite calculus, that work is equal to 0. So in order for work to happen in one of these closed systems, the volume has to change. So anytime you get constant volume, you have 0 work. So our work in process 2 is 0. So now we can rearrange the first law to find equations that tell us the heat transfer in my first process. That's going to be the mass times specific internal energy at 2 minus the same at 1 plus the work from 1 to 2. And in process 2, I have the same equation. It's just my state numbers change because now I'm going from state 2 to state 3. So I don't know the heat transfer for either of these processes. I do know the mass because it stays constant for my whole process. I don't know U1. I don't know U2. I don't know U3. I do know work from 1 to 2, and I know work from 2 to 3, which is 0. So if I could fix my states, if I knew the specific internal energies at state 1, state 2, and state 3, then I'd be able to find the answer to this problem. So now let's start fixing our states. We'll start with state 1. So we know that this is a subcooled liquid, and we know that the temperature is 20 degrees. So we're going to assume that this point, state 1, is the same, essentially, as if it was just jostled over a little bit to the right onto that subcooled liquid line. So we're going to say that U1 for our given temperature and pressure is approximately equal to UF at T1. So now I look at my two phase tables here. I find the line for 20 degrees, and I find UF. And I get that it's 83.95 kilojoules per kilogram. So now I have a value for U1. So now I put that value into my state table, and I'm ready to find the specific internal energy of state 2. Here, I know the pressure, and I know the specific volume. I also know that it's a two-phase mixture because I drew out my TV diagram. So here, I know that U2 should be UF plus X2 multiplied by UG minus UF. Unfortunately, I don't know the quality yet. So I could find U2 if I knew the quality, but I don't know the quality yet. So instead, I have to use the information that I know Remember, I know two independent intensive properties here, and one of those properties is specific volume. Now, specific volume follows the same equation with respect to quality, but now I know V2, I know Vf, and I know Vg. So I can get an equation for x2 using my specific volume. I look this up on my table, and I find that x is equal to 0.94. Now that I know that the quality is 0.94, I can put that into my equation for specific internal energy. And I see that U2 is 419.9 plus 0.94, that's my quality, times 2087.6. This is all in kilojoules per kilogram. Or I find that U2 is 2,373.2 kilojoules per kilogram. So now the only state that I haven't fixed is state 3. I know that the pressure here is 4 bar and the specific volume is 1.57. From the diagram that I drew before, I know that state 3 is up here in the superheated vapor region. For superheated vapors, I know I'm going to have to find an interpolation factor unless I get lucky and I'm right on the line. So here's my table for superheated water vapor. I know that my specific volume is somewhere between 1.4685 and 1.5840. So I'm going to have to use specific volume to find my interpolation factor. Remember, when we do linear interpolation, it's really the same as this kind of graph. So I know my specific volume is 1.57. That's in between my range. I'm going to move that over and I'm going to use it to find the A value. And once I know A, then I can use A to find specific internal energy. So here's my equation for A. I know my specific value, my specific volume at state 2, and then I know the minimum and maximum ranges on my table. I'm using that interpolation factor to then find the specific internal energy for state 2. So in this case, I can find my interpolation factor. I plug in all the numbers that I get from the table, along with my known specific volume at state 3. And I find that my interpolation factor A is 0.88. So I now put that into my equation for specific internal energy. I'm using the same U min and U max that I read off the same line on the table. And I find that my specific internal energy is 4,234 kilojoules per kilogram. So I put that into my table, and now my state table is finished. And that means that I can take all this information from my state table, put it back into my two equations that I used for the first law on each of my processes, and find Q. So now all of these things are known except the heat transfer. So I don't know the heat transfer. I do know the mass. I know U1. I know U2. I know U3. And I know the work for both processes. So at this point, I'm just putting numbers into my calculator to find the heat transfer for process 1 and for process 2. So the heat transfer for process 1, I'm going to carry my units through here. I see that my kilograms in my first term are going to cancel. So I'm left with kilojoules plus kilojoules, which is good. That means no more unit conversion. And I find that I have a positive value for heat of 4,895 kilojoules. I remember my sign convention, hip to win. So this is heat in is positive. So heat is being added to my system. And this is what I think should happen because that's what the problem tells me, that I'm adding heat through both of these processes. Let's see about process number 2. Again, I use what I have from the first law. I know everything here. I check my units again, so it's going to be kilojoules plus kilojoules, but this second term here is really just 0. So here, I'm adding a little bit less heat than last time at 3,722 kilojoules. So now I can find the total work and the total heat using my process table. So my total heat is the sum of the heat transfer from both of my processes. This was both positive, so I'm adding heat in both processes, and I get a total of 8,617 kilojoules. My total work is only the work from the first process, which is about 320 kilojoules. So this is a pretty good example of a multi-step first law type problem. So let's validate the work that we've done. We checked our units. They all make sense. Our work is in work, right? So this is an energy unit, kilojoules. So that's what we expect for units. Everywhere where we were fixing states, we were getting the right units. We only used incompressible assumptions for liquids. So we didn't have to use any kind of ideal gas law here. We checked all of our signs, so Q makes sense, it's the right sign. So the work is a positive value too. We know that work in is negative, so this must be work out. It's our system pushing out on the universe, and that makes sense too. Because in the first process, our mass was pushing that piston out. So that concludes another lecture of thermodynamics, and hopefully with this, we're just about ready to write the first exam.